thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier webinar series. This series provides information to ASHRAE Journal readers and to others about products and technology of interest to industry professionals. ASHRAE does not review supplier webinar presentations. The following presentation has been prepared by SimScale. The subject is Building Performance Analysis Simulations from your iPad. Today's speakers are Richard Choquet-Shular and Kyrie Derry. Richard is the product manager for architecture, engineering, and construction applications at SimScale and is now leading the deployment of new AI and machine learning features in SimScale. Kyrie is part of the application engineering team at SimScale with experience in both CFD, FEA, and electromagnetics. He has a background in civil engineering and had completed his master's studies in computational mechanics from TU Munich. Richard, the microphone is all yours.
Thank you, Drew, for the great introduction. And thanks for ASHRAE for giving us the opportunity to present today. I'm really excited to see that many attendees already. Before we start, let's have a quick organizational note. During the presentation, you will have the option to post questions with the question and Q&A panel. Please make use of it in case you have any technical issues, you don't have sound, video issues, and so on. But also if you have any questions about the presentation and the topics of today's webinar. And towards the end, we'll spare like 15, maybe 20 minutes to hopefully answer all of your questions. And with that, let's start with today's topic, building performance analysis simulations from your iPad. For the ones that really don't know what SimScale is, in a single sentence, pretty long sentence, SimScale empowers engineers to innovate faster by making high-fidelity engineering simulation technically and economically truly accessible at any scale to architects and engineers. So that's basically our motto. But what does it actually mean? So SimScale is a cloud-native simulation platform. It's one platform where you have a broad set of physics. You can analyze flow phenomena, heat transfer, radiation, including humidity effects, and much more. It's a platform that is made for all users, for very early stage use cases, but also very late stage verification analysis. It's made for connecting people on one project that worked collaboratively together and not working in silos. With SimScale being cloud native, you have direct access to the tool. You just need a web browser, no installation. You don't need to ask an admin to enable you to install new software. You don't need to connect via VPN or remote desktop. It's just there in your browser. You just need to log in. Since it's really cloud native, we enable full collaboration within SimScale. Think of it like Google Docs style sharing and collaborating on projects. You can work together with your colleagues on a new design, share ideas, help each other out, make design decisions together. And in a case you are stuck, you need some support, we have an industry-leading in-product support. There's a chat box. Quickly open the chat. Within a few seconds, you can share your project with SimScale. You don't need to download any data. Just click a button, and the project is shared with our support agents, and they're here to help you and solve your problem immediately. Finally, SimScale can run simulations at basically any scale. You can use it for very small, very early stage projects, but at the same time, you can run high fidelity transient CFD simulations with hundreds of millions of cells. And not only you can run very large cases, but you can also run the full set of design space options basically in parallel. If you're running HVAC optimization studies, you can run all the different flow rates at the same time, for example, all made available through the power of cloud computing. And with all of this, SimScale is still cost effective. It has a very low total cost of ownership, and is economically viable for a single user, but also for large organizations with hundreds of seats. So that's, in a nutshell, more or less what SimScale is. Now on today's application. Today we want to focus on HVAC design and how SimScale can be used to really make informed decisions on how to optimize HVAC designs for different use cases. The use case today is a shopping mall, a central mall of a shopping hall. We want to really optimize the HVAC system, see how the ventilation is behaving under different conditions with or without solar load, with humidity, and how these different modeling effects will actually affect the performance of the HVAC system. My colleague Harry will actually show you how you can quickly set up this analysis and how you can run a series of design simulations with just a few clicks, including the CAD import simulation setup, and most importantly, the result analysis and the decision-making process to actually can make an optimized design decision being informed with simulation data. And with that, I'm handing over to Harry. Thank you.
Thank you, Richard, for the informative introduction, and a warm welcome from my side to everyone attending the webinar today. Now, let's take a look at how SimScale can be used to assess the ventilation and thermal comfort by using an example of the shopping mall. So as you see here on the right-hand side, we have the shopping mall model that we use for our simulations. The shops in the shopping mall are cut out from the model. In reality, they should be extending through the rectangular extrusions on the sides. In this particular model, we have a glass dome and a facade, which allow solar energy to be transmitted through them. We also have roof vents on the sides of the dome and on the roof. The overall heat gain, which represented by humans, equipment, lighting, etc., is spread out over the volume of the shopping mall. And in this case, we are simulating a mid-season scenario in New York during September, where the ambient temperature outside is around 21 degrees Celsius. Throughout the technical demonstration, which I will carry out in a few seconds, we will touch on and answer various questions such as, how can I simulate the ventilation efficiency accurately inside a given space? What sort of outputs can I visualize, such as temperature, velocity, mean age of air, etc.? Moreover, can CFD be actually leveraged to optimize thermal comfort inside a closed space? But not only that, but to what level of detail can we actually analyze these cases? And lastly, how to incorporate solar loading and humidity into the CFD simulations? Is it a difficult workflow? Is it cumbersome, or is it actually quite easy? All of these questions we will touch on in the technical demonstration. Moreover, these questions would really invite us to explore how CFD can be used to obtain a more holistic understanding of the indoor environmental conditions by analyzing sub-zone level analysis. So now we will jump into the SimScale platform. In order to access SimScale, first you would need to create an account if you don't have one, and then you can log into that account via your username and password. Now once logged in, you get prompted with the dashboard. And the dashboard is essentially the place where you can store all of your projects that you have simulated. Those projects can be, of course, nicely organized in folders, and they can as well be organized between different teams in your organization, where each team then would have a specific side of the simulations that they focus on. Now, of course, any of those projects that you have ran can be easily shared between different colleagues. This is something that I will touch on a little bit more in detail later in the presentation. A nice to know thing as well is that with SimScale, you have unlimited storage, so you do not have to worry about storage space. You can have as many simulations as needed on the SimScale workbench. All right, so now let's make a transition and take a deeper look into how SimScale can be used to assess the internal thermal comfort and the performance and efficiency of a ventilation system inside a closed space. At the moment, we are inside the SimScale post-processor for the first simulations that we have run. This simulation on the shopping mall includes both solar load and humidity. Now, before we dive deeper into the results and make some observations and so on, I would like first just to highlight the cloud native aspect of SimScale. As you see, I'm directly using it on a browser. You can access SimScale from anywhere in the world at any time via an internet connection and a browser. Now, this becomes quite important because we know CFD simulations can really be sometimes quite computationally expensive and demanding. And for that, you would need to accommodate those simulations with a proper workstations or an HPC setup and so on. With SimScale, this cost of hardware investment is completely eliminated right away because all of your simulations do not use the local computer resources that you're running on, but rather uses the resources of the cloud instances that we have. This makes the simulation work much more efficient, especially because you can run as well simulations in parallel, which is something I'll show that later in the demonstration. Cool. Now let's understand what are those results that we are visualizing. So first of all, before diving into the results, the north direction of the shopping mall is aligned with the y direction, and the solar load rays are coming from the southwesterly direction, so essentially from here. And what we are visualizing at the moment is the internal solar load field plotted on the surfaces, which essentially represents what's the amount of total heat flux gained as heat on those particular surfaces. And we're also visualizing the temperature distribution of the particle traces as they exit from the HVAC units. Now we can immediately make one observation here that through this air curtain, which is just near the glass entrance, the air curtain is applying temperature at 18 Celsius degrees as shown by the legend. As it interacts with the surfaces that are getting affected by the solar load, essentially the temperatures rise from 18 Celsius degrees to around 24 Celsius degrees. Moreover, we can take another look as well into the other surfaces that were affected by solar load. So essentially the solar rays again were coming from this particular angle, and we can clearly use this information to identify at a certain time, at a certain day, what areas of concentration essentially would be affected the most and so on. Now, further insights can be made into this simulation by making other plots that shows the overall temperature distribution, let's say, inside the space. So for example, with this plot over here, we're looking at a vertical plot of the temperature distribution, and we can clearly see a lot of hot air is being trapped on top of the glass dome. Let's also assess what is the overall predicted mean vote inside space. We can take the example of the second floor. So this is a cutting plane on the first floor, on the human level. Overall, this is a uniform distribution of a predicted mean vote, and it's lying in between the comfortable range between minus 0.5 and 0.5. What I would also always like to investigate is the overall mean age of air inside the space, because that essentially gives us an idea to the overall residence time of a particle inside the model. Now, we can clearly see again, there is also, which correlates as well to the hot temperatures being trapped as they rise near the glass dome. We have a higher mean age of air in that area, which could be okay because humans are not going to be concentrated on the top of the glass dome. However, we see clearly that throughout the shopping mall, we have an average mean age of fluid of around, let's say, 1,000 seconds, more or less. Of course, this information can then be used to calculate how many exchanges per hour can occur inside a certain space. All right. Now, after making some observations on this particular model, one scenario that could occur is that I would like to assess different ventilation strategies, for example. And for that purpose, I might need to do some CAD modifications. So let's take, for example, that I am working in a company where the architectural team essentially is responsible for doing those CAD modifications. So now I have my first results, I made some few observations, and now I would like to instruct my architectural team, or essentially the CAD designers, to make some CAD modifications for me. And the process for this is quite simple. What I can do now is I can essentially share this project with my colleague. Let's take, for example, that my colleague Richard is an expert CAD designer, and I would like him to do some CAD modifications for me. I can provide him with either view, copy, or edit access. In this case, I'll give him edit access because I would like him to import the modified CAD model into this simulation right away. After the share process is done, which is essentially instantaneous, Richard would have received an email from me indicating that a project had been shared with him. And then he would go about importing the new CAD model into this project. And this brings us now to the discussion to what CAD tools does SimScale support. Now, SimScale support almost all native CAD formats, Rhino, Revit, SketchUp being some of them. Moreover, users of common thermal energy modeling tools like Tool, IES, E+, Design Builder, etc. would find SimScale easy to use, and their CAD models can be also imported into SimScale. For example, we have a proven workflow with importing Tool object files into SimScale. We actually have a past webinar for this as well. Now, after importing the CAD model, you can access it directly in the geometry tree. And here the CAD modifications that we have made were mainly essentially adding 3 equally spaced controllable roof vents on the top of the glass dome. And this is mainly to allow us to investigate different ventilation strategies. We will talk a little bit more on this later when we check the results. Now, the next step would be to go ahead and create a simulation. SimScale is a multiple physics platform, so you can run simulations on flow, structural, and even electromagnetics. For the context of what we are trying to solve today, the solver of interest would be the conjugate heat transfer, as it allows us to simulate heat transfer by convection, radiation, and conduction all together, and it couples the flow and thermal side of things. Now, I would like to highlight how easy it is to add and remove complexity to such a simulation. With a few clicks, I can add radiation, solar load, and humidity in order to increase the fidelity of the simulation that I'm trying to run. Moreover, for the interest of time, I wouldn't go over the simulation setup now from scratch, but I would show the setup of a simulation that we already made. And to set up for this, what you can also always benefit from is the fact that you don't need to set up a new simulation usually from scratch. If you have a template, let's say, of one simulation that you've run, and you know the setup is going to be used the same for the new modified design, but you're just changing the geometry, you can make use of this template that you have here, duplicate it, and then change the name and finally change the geometry that you would like to simulate, and then go ahead and run that simulation. Now, if we go back to the setup of the simulation with the controllable roof vents on the top, I can quickly show you, for example, how easy it is to set up the solar calculator. So here we see the direction of the solar rays. You just type in your location, choose the date and time, and define your solar load parameters. Next, for example, if we would like to define the HVAC supply flow rate, let's say, for our units, you can either run a specific point or you can run various different points together at the same time. And this is beneficial if you would like to explore, let's say, different operating conditions for different scenarios, and so on. Let's add, for example, one more. Those could be 4, those could be 100. And you can import them directly via CSV file as well, so you do not have to type them manually. When you define a parametric simulation like this, what essentially happens is that you would be able to run those simulations directly in parallel at the same time. So for example, if one simulation finishes in 1 hour, all of those simulations are going to finish in 1 hour. So now each one of those is fired onto a different virtual machine on the cloud. Now, luckily, we don't need to wait until this simulation finishes. I already have a working simulation. We can now jump in and compare the results of those. Cool. So now what we are looking at, again, inside the post processor, on the left-hand side, we are looking at the simulation with solar load and humidity. So that's the base case that we have simulated. And then on the right-hand side, we have the case where we added the controllable roof vents on the top. Now, from the particle traces, we can already see that near the top of the dome, the temperature of the air particles moving is actually much hotter than the case with controllable roof vents because there is no air accumulation as such anymore as in the other case. We can take a deeper look into this actually by making a cutting plane and then investigating the side view of this. So in this particular case, essentially, when we compare them, what we are really doing is that we are investigating a different ventilation strategy on this side that incorporates stack effects in this case. So this completely changes the internal air movement patterns, the efficacy of ventilation, and hence the thermal comfort and energy consumption. So for example, in the original model, there is a lot of trapped hot air and thermal stratification, which could re-radiate heat inwards in summer and decrease comfort and perhaps as well increasing the cooling load. Conversely, however, in winter this might be useful to reduce heating load. Therefore, having controllable roof vents seems like a good idea to give additional flexibility. We can even take a look as well to how this correlates with the predicted mean vote on one of the levels. So for example, we can take a look here at the second floor human level. We see even with the controllable roof vents implemented, we still have a comfortable environment as the predicted mean vote falls between minus 0.5 and 0.5 for both cases. Additionally, we can also investigate the temperature distribution inside at a particular level by simply changing the parameter. And actually, this also brings me to the topic that with those simulations, the nice thing about CFD is that it really gives you the opportunity to investigate what is happening on a subzone level. So it gives you this information at every single point. What is the temperature? What's the velocity, the pressure, the absolute humidity, the mean age of air, etc., etc. So the potential of how CFD can be used to enhance essentially the overall thermal comfort inside the space, to improve the sustainability of a building design and so on, is indeed quite vast. And with this, I would like to end this technical demonstration, and now we jump back to the slides. Cool, perfect. And now that we have finished with the technical demonstration, I would like to pass over again to my colleague Richard, who will talk about some of the applications inside the SimScale platform that relates to the topics that we are talking about today. Back to you, Richard.
Great, thank you, Kari. Great presentation. It was really showing how efficiently you can analyze different design options, different HVAC variants, add these controllable roof vents and see how they really change the flow patterns, the hot air stacking or not towards the roof of the building. It was really very, very insightful. Next, I would like to take a step back and look at the bigger picture again on, besides this particular topic, what are other use cases that we have available and that people and customers specifically are using SimScale for in the professional work. If we start on the outside on the microclimate and environmental analysis, here we see a subset of applications that our customers are using SimScale for. On the top left, for example, we see Zahadid Architects, one of their example use cases that we can publish, which is a pressure wind comfort analysis for the Oppo headquarters in China. So there they use SimScale to analyze whether there would be any adverse, uncomfortable, or even unsafe wind conditions created by the newly designed tall tower. Luckily, they weren't, so they were happy with that. On the lower left side, we see completely different environmental analysis use case, reservoir filling analysis that you can run with SimScale with the new multi-phase solver. You can really see transiently how such a water reservoir would fill with water and what the patterns would be, how the water would run out of it, and so forth. And for example, on the lower right side, we see complete microclimate analysis, UTCI evaluation for an airport that combines basically wind analysis together with solar, with temperature, humidity, to get a holistic view on the climate conditions locally around the building. And now if you go back inside the building for the building performance and environmental analysis inside the building, we see again on the top left the similar use case we already talked about today, a theater thermal comfort analysis. We're really interested in the thermal comfort of the occupants, but you can go also in more detail and analyze, for example, the HVAC system or subsystem and optimize flow paths, for example, through the duct system, which we see here is in the top center from our customer Fessmann. Not only that, we could also look on the structural side of things and analyze the facade 3D thermal bridging and see if there's a risk, for example, for condensation and mold growing on the inside of the facade and cold conditions typically. Or on the lower right side, a more traditional analysis where CFD has been used already since a longer time for data center design and optimization. So we want to find the optimal design so we have the lowest energy use to keep all of the server racks below critical temperatures at all times of the years and under very various operating conditions. But besides these traditional use cases and also the use of SimScale, as we've seen how Kari demoed it today through the web browser, there's also another option how SimScale is delivered, and it's namely through third-party integrations. On the left, we see an integration example that was co-developed with our customer Thunder Massetti. They developed a Rhino plugin. So within Rhino, you can run pedestrian wind comfort and building wind load analysis directly. So you can set up multiple scenarios, building options within Rhino, and then with Nuada CFD, you can set up a pedestrian wind comfort analysis that analyzes at the same time all your potentially 4, 5, 6 different design options. It uses for this SimScale and a powerful cloud computation backend to run all of these analyses and bring back the results into Rhino, where you can then analyze them and choose the best design option. All of this without even leaving Rhino. Or on the right side, our partnership with Esri, where we created a GIS embedded result visualization. So within the ArcGIS tool, you could plug in the results you would get from SimScale, for example, for the pedestrian wind comfort, and municipalities could assess, for example, new zoning concepts and how they would impact, for example, the wind comfort conditions in an urban area. And finally, the example in the middle, we see our NVIDIA Omniverse connector. So with the Omniverse connector, you can get your scenes from Omniverse, which plugs into many different design tools such as Rhino, Revit, SketchUp, and so on. Collect your design and send it to SimScale to be analyzed. And then you could also pull back the results into Omniverse and then use really its powerful visualization options to really make visual sense also of the results. So here we can see an example of the results we got from Khairi on the shopping mall center. And you could, for example, then use advanced VR technology where you can really go inside the building virtually and assess the operating conditions, see the airflow really in detail, and come up with new ideas, better ideas, how to do the HVAC system design. And obviously, all of this is only relevant if customers are actually using it. So here we see a use case from our customer, Smart Louver. They're using SimScale to do the ventilation louver design. Want to assess the discharge coefficient under certain conditions. Use it for analyzing the pressure drop across the louvers, but also under maybe unusual conditions to assess how does the behavior change when we have maybe solar load on it. If the louvers heat up, will it change the airflow patterns and so on. Another good example of use of SimScale from customers is Monodrone. So they're designing complete HVAC units, as we can see on the example here on the left side. And they used CFD particularly to optimize the air paths inside the unit. And with that, they could increase the ventilation flow rates through the HVAC unit, but also they could reduce the fan power consumption by over 50%. And this really marks a significant reduction in power use of the unit throughout the lifetime. And finally, one example I really like a lot is from our customer Kohler Ronan. They used SimScale to assess and optimize the redesign on the ventilation system of the David Jaffin Hall in the Lincoln Center in New York. And they used SimScale to really first assess the old ventilation strategy and then make an optimized decision on new ventilation strategies with respect to ideal distribution of air, HVAC energy savings, and also the comfort, obviously, of the people watching the concerts. And we have really here a great quote from our customer, from Madhav Munshi, who used SimScale to do these design evaluations. And he said that the benefit of SimScale is the ability to link advanced CFD and cloud energy savings to combined with the energy saving from the thermal energy modeling. So with this, they could optimize for comfort in these sensitive spaces, like the large theaters here, where they have really constrained structural and acoustic options. And having access to the right tool at the right time is really critical to ensure the building performance. You can read about a lot more case studies if you want to maybe find exactly your use case that you're interested in and see how SimScale customers have solved this. You can just go to simscale.com/customers and have a look around. And finally, I wanted to highlight a few of the new feature updates that we have shipped in the last months that might be relevant for you before we go on to the Q&A session. I remind you to just, while I'm talking, paste in your question, and we try in the end to really answer all of your questions. We have a new addition on SimScale since recently, which is a new proprietary solver dedicated to the design of pumps and fans. This solver technology enables really efficient and fast turnaround times for not only steady state, but also transient simulations of pumps, but also multi-phase flows. You can not only run the analysis of a single operating point of these pumps and turbochargers or the like, but you can also directly run complete performance curves within a click. So this is fully automated to just with a very simple setup get the complete performance curve of your pump or fan design. Another important new addition specifically on the indoor environmental modeling is the new additions to the solar module. We can now use it together with fluid and solids in our designs. So we can use actual solid models for the furniture, for the walls, for every piece of solid that's actually part of the design. And this enables us to really be more efficient with the simulation setup, but get even more accurate also with our results, as we can really take into account the actual local behavior that these solids have in our actual simulation. So if the sun is hitting the solids, it's heating up, it's radiating heat back into the domain and so forth. This is all modeled in the new coupled conjugate heat transfer solver with the solar module. Also, since recently, since actually a couple of weeks, we have fully resolved local mean radiant temperature results and operative temperature. So instead of having a uniform averaged mean radiant temperature across the domain, we now really compute locally at every point the local mean radiant temperature. This is specifically important in such large domains as we have seen today, as we see quite a difference, especially the operative temperature, but also the mean radiant temperature throughout the domain. And obviously this was also validated across well-known references to be sure we're getting accurate results as well. And for me, one of the most interesting new additions is the full solution of humidity on SimScale. This is something that not every CFD tool can do very efficiently. With this new addition, we can add humidity not only to inlets and outlets of our domain, but also as sources inside our flow domain. So for example, we can take into account the humidity that is generated by plants in our environment that we want to analyze, or by free surfaces from pools that emit humidity to the air around it. There's a very extensive documentation on this available on SimScale, and you really can use this to unlock new types of modeling that wasn't available before. For example, in this case, vertical farming is a very good use case here, because there it's really important to model accurately all the different components that are needed to optimize for the best yield possible in a very confined space. So there you really need to optimize the ventilation strategy and so on to really get the most out of your energy spend, and to ensure that the plants grow evenly distributed on all of your levels. And with that, we are through the main content, and I'm happy to invite now Nagman, Dr. Nagman Khan, to the discussion. He's our product marketing manager at SimScale, and he will lead now through this Q&A session. Hello, Nagman.
Ricard and Khairi, many thanks for a fantastic presentation. Can you hear me?
Yes, we can.
Yep, loud and clear.
Excellent. We have a lot of questions coming in, and we have about 20 minutes. So thank you for all the questions. We will try and get through all of them. Ricard and Khairi, because there's a lot of questions, I'm going to cluster them into topics, okay? Because some of them are very similar. And I want to start with something that's quite central to this presentation, which is about simulation in the cloud. So we've had several people asking, what does it mean exactly? What do you mean simulation in the cloud? How can you perform building performance simulations in an iPad? Okay, and really the gist of this question is traditional simulation software, like one of our attendees has asked, has always been quite desktop. You know, the AEC industry is very desktop heavy. We have large models, you know, they take up a lot of file sizes, they're big complex model, a lot of geometry, a lot of meshing. So doing CFD also is a very desktop heavy software. So I just want to go back a step. Khairi, maybe I'll start with you since you gave the demo. If you could just talk a bit about what it means to be in the cloud, simulation in the cloud, specifically for CFD. And I'd like Ricard also to comment on that afterwards. Thank you.
Yeah, absolutely. Absolutely. So basically, when we talk about the cloud, and this is really an answer from a person who was using desktop applications quite extensively, especially during my master thesis. We used to run simulations that usually takes like 5 days, and we have to wait for each simulation to finish to run another one. And then the moment I got introduced to cloud simulations, from my experience, what I realized is really different is, first of all, the overall experience. When you try to open the application, it doesn't get stuck. You don't worry about, is that consuming all of my local computer resources, because basically you're just opening a web browser like you're opening Google or YouTube or whatever you have on the browser, right? So that's something. So it's very easily accessible. The login for it is also very easy. The things that comes with cloud native solution is scalability. Like, for example, it's really easy to scale up the use of simulations in an organization when it's on the cloud, because first of all, you don't have to worry about buying many workstations, nor setting up an HPC, nor arranging for software updates each time with the IT departments. So all of that hassle is really gone. And then you have the collaboration side of things. We saw in the technical demonstration earlier how easy it is by literally a click of a button, typing an email of a person, and then sharing that project, let's say from the US to Germany in a second. In the old way, you would have to download the data, put in Google Drive or OneDrive or whatever, share that information, download again. I think you get the point, right? And moreover, with our solution being on the cloud, we have the ability to provide a level of support that, in my opinion, does not exist in any other tool. Because we do staff specifically engineers to conduct these support. And essentially, whenever you write a question, of course, we give much more importance to our professional clients, and we aim in always providing answers in minutes. And the main goal is to really make sure that you're successful. In my words, that's how I would summarize a cloud solution. And in the end, we also do have the capabilities that allows us to run heavy, complex simulations. And yeah, I think that's how I would summarize it from my word.
And Ricard, could you add to that? Maybe also explain a bit about, yeah, go ahead.
Yeah, I mean, there's not much to add. I mean, Harry really covered everything, right? From the point where you get started with the tool, like the hardware installation, getting people enabled on it, being distributed, right? Sharing data, all of this is made easy. Yeah, so cloud simulation just means that you have direct access to the tool. You don't need to send around the data. Yeah, you have everything where you need it and in a centralized place. Right? There's no version 1 that's sent to someone that has then version 1.1, sends it back, version 1.2, and no one knows what is the latest version and so on, right? So there's no one hard disk here that someone has on this local computer. It's yeah, makes a lot of things.
It's really
easier.
something. Yeah, thank you, Ricard. It's really something you all need to try, right? Where Ricard will explain at the end how to get started with SimScale. It's very easy. There's a free platform. Sign up, and you can. It's just a simple, like Harry said, login to a web browser, right? Just imagine you're logging into Netflix or something, and like we said, you can access that from an iPad on a train as long as you have an internet connection, because the simulations aren't actually done on your laptop or iPad, right? They're all done in the cloud. You're just interfacing with the platform through your web browser. Okay, I think there's a related question here, Ricard, while I have you here, about meshing. And one of the attendees is asking, again, we have big models, right? Some of them are quite complex. For example, Revit models, BIM models, and meshing's always been an issue. So a couple of questions I'll cluster together here for you, Ricard. One is, what kind of CAD file formats can be imported into SimScale? What are the kind of common CAD tools? And how do you treat meshing?
Sure. CAD file formats, we support many of the standard file formats or tools used in AEC, Rhino, Revit, SketchUp. We have workflows for all of them. You can also upload the native formats, right, for Rhino, for example, or you can use neutral formats for CAD Exchange, up to a very simplified STL file, for example, right? So there's many options, and for all tools available, we have a workflow where you can easily bring your CAD to SimScale. We have even direct cloud integrations with tools like Onshape, right, where you can just pull your CAD in without the need to download it to any local hardware.
Yeah.
Regarding meshing, yeah, we have a focus on automating as much as possible and having the least required user interaction, but still giving the user the flexibility that they need in certain corner cases to really go into much detail and refine locally as they like. So we have more or less smart mechanism to define local refinements, local cell sizes based on the simulation setup. So we first do the simulation setup on a CAD model, and based on the information from that, our meshing algorithm takes this into account. For example, if you have a wall, right, it automatically defines boundary layers on that wall. If there's an inlet, we do a refinement of the cells towards the inlet domain, right, from the outside. So we have a refinement there where we expect the flow to come into the domain. So there's a bunch of different automations we have in the background that make sure that the default mesh you get from SimScale without much user interaction is already a pretty good mesh to start with and will be sufficient for most of the cases. And you can just decide if you want to start very coarse or already go with a fine mesh.
Yeah, brilliant. And that is a huge advantage. I mean, importing CAD geometry, preparing it, and meshing always been the upstream bottlenecks before you even get to the simulation, right? Before you even get to the fun stuff. A lot of people used to get stuck in importing and cleaning CAD and the meshing. And that's something we work really hard on. And you have to see it to believe it, right? So please sign up, send us your CAD models. We can help you import them and get started in minutes. Ricard, while you're here, you mentioned integrations. One of the attendees was asking about Cove Tool. And I know you did a webinar with Cove Tool a few months ago. Wonder if you could just mention that in just a 30 seconds, how that works.
Yeah, so we have a webinar with them. I can highly recommend that to you to check it out. So basically, we have a file format connection via an OBJ file, so we can export from there to an OBJ. I don't know, meanwhile, it might be even STL possible. And then you upload the STL to SimScale and run your wind comfort studies, for example. That's what we used in that case, but you can also use it for indoor studies as well.
Perfect. Khairi, a couple of questions for you here. One is on smoke smoke simulations, for example, in car parks, in tunnel. So one of our attendees is asking about this and simulating jets from fans in places like tunnels and car parks, right? So maybe we'll start with that. And the second part of that related question to that is templates, which is a great question from Colin. So the question is, if I create a template for one project, can I use the same template on a different project?
Perfect, cool. So let's start first with the first question, which is, can SimScale be used to support smoke ventilations? And the answer to that is yes. So there are certain ways and there are certain approximations and assumptions that we make in order to run those simulations. So for example, we have actually various different customers that use SimScale for these applications, like in car parks or even tunnels, where basically the idea is that we simulate the air domain of that, let's say, that car park, and we assume the smoke is basically a contaminant that is being driven by the air. So we track that by what's called a passive scalar. So we assume that the smoke or the CO2 is basically having similar densities to the air. And then with that, we track how overall its concentration is distributed inside. Of course, with this, simulations, usually what our clients do is that they like to investigate which positions exactly are best to place those jet fans, for example. And then we can those, of course, replicate them using a momentum sources. So basically we can add virtual bodies that represents those jet fans that supply a constant stream of velocity of that body so that we can really assess the overall ventilation inside that space. And where do we get areas of low concentration, high concentration, and so on. So I would really invite you to actually get in touch with us, and then I could be more than happy to actually show you how such a simulation for smoke contaminants inside a car park would look like live on the SimScale platform. So that was for question number one. And question number two was, if I remember correctly, Lagman, was on the templates, right?
On templates, exactly, yeah.
Cool. So when you create a project inside SimScale, the details of that project are stored inside that project itself. So basically, if you create a template inside that project, you can use that template only inside that project, right? So you can have various different simulations where you are using the same template. However, transferring that template between various different projects is not yet supported. I don't know, Richard, if you would like to add something on that as well.
Yeah, so basically how customers use that is they create specific template projects for specific use cases. So they typically have a shared folder with templates for their team, and then everyone, whenever they have a use case that was solved before, will import that project or make a copy of the template project and then work in this new project with it. So you can typically create the template project and then pull in from that to do your work on the specific use case.
Exactly.
Brilliant. Ricard, you showed a slide earlier. I think it was the case study with Monodraft, and there were some swirl diffusers there. We have a attendee asking how complex can you get with the geometry? For example, some diffuser types can be, very complex in terms of their 3D shape and geometry. And also, can you account for things like furniture and people to account for, mass and thermal effects?
Yes, sure. I mean, we can get very complex, right? We can have really details in the geometry also for the diffusers. We can really model the diffuser in 3D and analyze the patterns through it as you like. It's just in the end, it's the question of effort versus benefit, right? So these simulations can be complex after some point, right? And can just take time. So it's sometimes the matter of judgment if a high detail is needed or not. But in principle, you can really go with the very detailed manufacturing model, more or less, solve it on SimScale and get the detailed flow patterns, for example, like for this swirl diffuser here. You could also then get from a detailed model the flow behavior exported and use it as a boundary condition in a larger room, for example, right? That if you have a large atrium, you don't want to model all these diffusers in detail, but rather the effect of those. And that's typically how we do it, we define a specific custom boundary condition that mimics the behavior of this diffuser without resolving all the details in a large space.
Perfect. Kyrie, let's go back to the shopping mall model. So an attendee is asking if you wanted to model CO2 in there and visualized, the distribution of CO2, what would be the easiest way of doing that? I know this is something Kola Ronan also did on the case study that Ricard showed.
So the easiest way to do that would be to use what we call passive scalars. So this is the same concept that I have touched on in relation to smoke. So we would assume that CO2 is essentially a contaminant. Like, for example, imagine a stream of water and you put a dye of color. You visualize how that dye moves inside the water. So we would assume the same thing. So that passive scalar would essentially, we would track how it moves inside the domain and essentially assess the overall concentration and distribution of it. And adding that into the simulation is actually very easy. It's literally enabling one little setting. So it's basically 2 clicks max, and then you would be able to track the concentration. Moreover, if you have sources of CO2 inside your domain, you can actually define those as well. So you can really go into the depth of it when you want to set up these simulations with the CO2.
Yeah, perfect. Interesting question, Ricard, on validation. So we have a few people asking about the quality of the results, right, from SimScale when it comes to indoor simulation, for example. I guess it's a general question about the SimScale solvers. How well validated are they, and where can people see more information on this?
Yeah. So SimScale uses a range of different solvers. Some are open source, some are in-house solvers, and some are third-party solvers. All of them are validated. We have an extensive validation suite that is publicly available on our website. You can have a look at those. Each new feature is also, again, validated, like, for example, we see here for the mean radiant temperature. So yeah, in that sense, it's as validated as other commercial tools that you know, and also open source tools like OpenFOAM and others that have their own validation suite. Often it just depends on how the tool is actually used in practice, right? If you can in practice get accurate results and not necessarily only on academic examples on very simplified models.
Yeah, brilliant. And we have a validation section on our website, like was mentioned. You can feel free to see a lot of studies published on there. Okay, I'll take questions for another 5 minutes, and then I'll hand back to Ricard for closing, because we're coming up to the top of the hour. We still have a lot of questions to get through, so thank you for those. Let me take a few specific ones. We can do some quick answers perhaps, and then the last group of questions, because there's so many of them, we'll do about how to get started with SimScale. A lot of you are asking about pricing, academic plans, access for students as well. So we'll come back to that right at the end in a few minutes. So Ricard and Khairi, we have many people asking about using SimScale with thermal modeling tools. Someone mentioned Design Builder, someone's mentioned IES, we've already mentioned Cove 2. Okay, a kind of a typical workflow, or how do existing clients use SimScale to elaborate on the studies they're performing in the thermal energy modeling tools for compliance, perhaps, if someone's working on a LEED or ASHRAE project, perhaps BREEAM. And I know we've seen examples of this already. Please share your thoughts quickly.
Yeah, I think energy modeling tools are great for assessing long periods, right? To assess what is the overall energy use of a building over the full year, right? That's not something you can do with CFD. CFD is good if you want to have a look at one specific point in time of one scenario and see what is the detailed behavior within the space, right? How do people feel when they sit next to the window versus a bit lower to the left, where there might be some downdraft from some inlet from the HVAC system and so on, or outlet. So that's the difference. And the combination of tools is typically used where we use the results of one to feed it into the other tool. For example, what you can use SimScale for is you get the accurate representation of the pressure coefficients on the building facade. that takes into account the actual surrounding buildings as well, as they have a large influence sometimes on the actual pressure coefficients of your building of interest. And then you take these pressure coefficients to feed them into your building energy modeling tool, where you can then assess the natural ventilation capacity over the year and if natural ventilation is a feasible strategy for your design. And there can be large differences if you use the just estimated profile for the pressure coefficients analytically, or you actually take into account the surrounding buildings. That's one sample use case, for example, that we often have.
Perfect. We have a related question to that. One of the attendees is asking, can we use results reports from SimScale to achieve targeted points in lead credit categories? So we have a webinar that we did last year specifically on this, using CFD for lead and well credits. Okay. And what we'll do as a follow-up to this email, we'll send you a link to that webinar. It's actually published on YouTube, and you can see in more detail exactly what Ricardo has been talking about. We can't go into detail right now because we only have 3 minutes left, but it is covered there. Okay, so Ibrahim, if you look at that and get in touch with us if there's anything more specific on that. We had related questions about pricing now and access. Maybe Khairi, last question for you is, how does someone get started with SimScale? So you'll have a lot of people here who are used to using, CAD tools, BIM tools, and also thermal energy modeling tools, but might never have actually tried a CFD tool for many reasons. What's the best way for them to get started with SimScale?
Well, it's actually very easy to start with SimScale. So I would kindly invite you really to just Google simscale.com, create an account. We have a free community version which you can play around with. We have a public domain as well where you can see many people what they have simulated. And you have essentially a starting journey as you log into your SimScale account. You can start with a tutorial. We have various different tutorials. So usually the process should be very simple. Just log in, type in SimScale on Google, go to the website, and just create an account. And then directly you would be directed into the dashboard essentially and the public community where you have a free version that you can run some simulations on.
Fantastic. And Ricard, I'll state the last question and also hand over to you for closing remarks. So many people have asked is the difference between, the free trial, the academic plan, professional pricing. If you could just comment a little bit on, the kind of SaaS pricing and that model related to the cloud, that'd be great. And then I'll leave it to you for closing remarks. Thank you.
Perfect. Thank you, Nagman. Yeah, so a starting point with SimScale can be the free plan. The free plan is basically a trial where you have a limited amount of simulations for free, where you can start to explore SimScale's capabilities. You will be simulating in the public domain, so everything that you simulate should not be confidential in that part, but you can use basically almost all the functionalities. We have the academic plans. They're very useful, for students, but also teachers. That is a almost free plan, basically specifically dedicated to universities, students, schools. You can get in touch with us and get access to your university. And there's the professional plan, where you typically have a yearly license of SimScale, where you can then have access to the full capabilities, where you can have basically an unlimited amount of parallel simulations. You have all the solvers available that we have on SimScale. You run private projects. That's very important. They are not shared with anyone else, not even with our support, unless you explicitly give your consent and share this specific project with our support agents. And yeah, we can also talk about NDAs if you have very specific requirements on the security level, but we're already employing industry standard SSL security for that you also know from your banking system and so on. If you trust your bank to do online banking, you would also trust the same standards to do simulations and keep your data private. So these are more or less the options to get started. You can reach out to us, to the presenters today. You find us LinkedIn everywhere, or directly contact sales@simscale.com to get in contact. We'll also write to you and send you the recording of today's webinar. And there you can also answer to get in touch with us if you want. And with that, thanks everyone for joining. It was really a pleasure to be here today and could present you SimScale. Thanks, Kari. Thanks, Nagman. It's great having you here. And thanks for Ashray for having us. And with that, I'm closing today's webinar, and maybe we'll see us again in the future for the next one. Thank you.
Thank you all for attending.